This is a brief tutorial on electrolytes and water solubility of ionic compounds. So let's look at electrolytes and how much they ionize. Aqueous solutions consist of a solute dissolved in water. These solutions can be classified into three basic categories. We've got non-electrolytes, and they are solutes that do not conduct electricity in water because they don't ionize. You need ions to conduct electricity. Covalent compounds like sugar, water, carbon dioxide are all good examples of non-electrolytes. Since water is a non-electrolyte, ions must be dissolved in it to conduct electricity. 100% pure water does not conduct electricity. For example, if we try to dissolve table sugar, sucrose, C12H22O11 into water, we get aqueous sucrose. It is designated by the AQ, but there are no ions, therefore no electrical conductivity. Stronger electrolytes are solutes that conduct electricity extremely well, especially in dilute aqueous solutions. That's because they completely or almost completely ionize, that is 100% or nearly 100% in dilute aqueous solutions. Some examples of strong electrolytes include strong water-soluble acids like hydrochloric or nitric acid and others, strong water-soluble bases like sodium hydroxide, potassium hydroxide, so on and so forth, and water-soluble ionic salts, sodium chloride, calcium bromide, so on and so forth, as long as they're soluble. We'll talk about which ones are and aren't a little bit later in the presentation. For example, hydrochloric acid, gas, unless it's dissolved in water, we dissolve it in water, we get H plus and Cl minus, both aqueous. Pretty much 100% ionization, so that's a strong electrolyte and a strong acid. Strong base, which is again water-soluble hydroxide salt, but it's going to split up into sodium plus and hydroxide minus, 100% ionization. A salt like calcium bromide dissolves in water to form calcium 2 plus 2 bromide minus ions. Again, 100% ionization. Be careful of the stoichiometry on the calcium bromide. If you got more than one ion, that 2 subscript becomes a 2 coefficient when you split the ions up. Weak electrolytes, they'll conduct electricity but poorly in dilute aqueous solution. That's because they only partially ionize. In many cases, this ionization is less than 10%. Some weak acids would include acetic acid, hydrofluoric acid, phosphoric acid. These are acids, but they ionize much less than 100%, usually less than 10%. Your weak bases, ammonia, some of your sparingly soluble metal hydroxides will ionize a little bit, and you get a little bit of basicity there. And some others. There's some water-soluble covalent salts, although that's not very common. Iron thiocyanate is a classical example of a cation anion pair that produce something that's a weak electrolyte. Now if you take acetic acid, notice I put double-headed arrows in there, produce H plus and acetate minus ion. But notice the double arrows indicate the reactants form the products, and the products can re-react to reform the reactants, so you never get complete ionization. There's ammonia. It actually chemically reacts with the water instead of ionizing directly, but it does produce ions of ammonium and hydroxide, again double-headed arrows. So let's talk a little bit more about strong and weak acids and bases. Acids are substances that are generally going to generate the H plus in an aqueous solution. There are some more sophisticated definitions, but that's what we'll stick with for now. Strong acids are strong electrolytes, and as we said, ionize 100%. If If you look at the example we used previously, the HCl is going to ionize into H plus and Cl minus. However, in aqueous solution, we typically write it as H3O plus, which is called the hydronium ion, because the H plus associates itself with one or more water molecules, and it's particularly in higher level courses that'll be a preferred representation. However, in organic solutions or non-aqueous solutions, H plus is perfectly fine. It exists by itself. So we could say alternately the HCl plus the water yields hydronium ion and chloride ion. So the difference between the top reaction and the bottom reaction is the addition of the equivalent of water to both sides. So the reaction is still balanced, but we just show that H plus is associated with water. Here are your 7 common strong acids: hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, chloric, even though chloric is kind of borderline depending on whose book you read, perchloric. Those are your common ones. There are some that maybe aren't as common, but this is be the list we'll stick with. Note the lack of hydrofluoric acid, HF. It is the group 7A element that actually forms a weak acid, so it's important to point out that that's not on this list. Weak acids are weak electrolytes, and therefore going to ionize less than 100% in water. Your weak inorganic acids are going to ionize reversibly, or what we call an equilibrium, usually 10% or less. There's our friend acetic acid, ionizing to form H plus and the acetate ion. Note the double-headed arrows indicating an equilibrium. Here are some common weak acids, and this is definitely not an all-inclusive list. You got hydrofluoric, as we mentioned before. You got acetic acid, which is the acid in vinegar. Notice there are 2 representations of that. The CH3COOH is popular in organic chemistry, which we'll save for another presentation. You got hydrocyanic, nitrous, carbonic, sulfurous, phosphoric, which you find in a lot of cola drinks and whatnot, and oxalic. Anions of weak acids tend to be weak bases, and we'll again save that for another day as well. Again, this list is very short. It shows a few of the common ones, but certainly not all-inclusive. Strong bases, like their counterparts, the strong acids, are strong electrolytes ionize 100%, but they're going to produce hydroxide in solution instead of H+. Here's the common strong bases. And what you'll notice is that they are group 1A and 2A metal hydroxides. Lithium, sodium, potassium, rubidium, cesium hydroxide. You could throw francium in, but you're likely not going to see that one. Then you got calcium, strontium, and barium hydroxide. Notice 2 hydroxides on each of those. I will say that the calcium, strontium, and barium hydroxides are not extremely soluble, although to the extent to which they're soluble, they behave as a strong base. So for example, sodium hydroxide in water forms sodium ion hydroxide ion, as we mentioned before. The calcium ion dissolves to form, or calcium hydroxide forms the calcium ion and 2 hydroxide ions. Again, note the stoichiometry, as we mentioned before. Weak bases are weak electrolytes, still produce hydroxide ion, but again, significantly less than 100%. Ammonia is the most common weak base. Ammonia plus water can form the ammonium ion and the hydroxide ion. So it's producing that hydroxide by chemical action, and that is an equilibrium. And as I mentioned before, the anions of weak acids are weak bases. But the cation corresponding to the ammonium ion, is a weak acid. So let's identify these as stronger electrolytes, weaker electrolytes, or non-electrolytes. A is sodium sulfate. It's a water-soluble salt, so we know it's a strong electrolyte. HCl is a strong acid, as we mentioned, strong electrolyte. Phosphoric acid is a weak acid, so a weak electrolyte. Carbon dioxide is a covalent compound, so a non-electrolyte. Now let's identify these as strong acids, strong bases, weak acids, or weak bases. A is nitric acid. That's a strong acid. It was on the list. So if you memorize the strong list, the other ones are weak. So strong acid. Acetic acid was our weak acid we've been talking about. Ammonia is a weak base. Again, if it's not on the strong list, it's weak. Sodium hydroxide was on our strong base list, so it is strong. Now what about water-soluble inorganic compounds? This will focus on the salts. Acids tend to be soluble. Ammonia is soluble, even though that's not a salt, we'll throw it in there. All of our compounds of sodium, potassium, ammonium are water soluble. There aren't any common exceptions to that. Nitrates and acetates are soluble. There are no common exceptions. Now, chlorides are generally soluble, but there are a few exceptions. Silver chloride and mercurous chloride are not soluble. Lead chloride is slightly soluble. If you form some interaction, you're still probably going to see a precipitate if you have any realistic concentrations if you see slightly soluble. But notice that it gives you a general rule and then an except. So if I see a chloride that's not on the except list, you could treat it as soluble. Bromides are typically soluble with a similar exception list. Silver and mercury or mercurous bromide is insoluble. Lead bromide, mercuric bromide, slightly soluble. Iodides are usually soluble with a pretty similar list of exceptions. Silver iodide, mercurous, mercuric, lead iodide, all insoluble. Sulfates are usually soluble with a slightly different list of exceptions. Lead sulfate, mercurous sulfate, strontium sulfate, barium sulfate are insoluble. Silver sulfate, calcium sulfate are slightly soluble. It means a little bit of dissolved, but not a really large amount. Now, sulfides tend to be insoluble, but there are a couple of exceptions. Sulfides formed with group 1A, 2A, and ammonium ion as the cation are soluble. Hydroxides tend to be insoluble except for group 1A, and barium, strontium, and calcium hydroxides tend to be slightly soluble. And so you don't really get a lot of solubility out of those. It's not like group 1A that's extremely soluble hydroxide. Those group 2As are less soluble. Barium's pretty soluble, but strontium and calcium are even less soluble. Carbonates, phosphates, and sulfites are insoluble except for group 1A and ammonium. Some covalent compounds like many of your gases, carbon dioxide, sulfur dioxide, hydrogen sulfide, are slightly soluble. You aren't going to get much solubility out of covalent gases in water at room temperature and normal pressures. So let's determine if the following are soluble in room temperature water. Now, some salts, like lead chloride, can become significantly more soluble in warm or hot water as opposed to cold water. But we're just talking about room temperature water here. And those were the rules we were talking about. All those rules were for room temperature water. Calcium sulfate was slightly soluble. The rule was most sulfates were soluble, but calcium was listed in the exceptions, and it was listed as slightly soluble. Ammonium sulfide, soluble. Sulfides are usually insoluble, but ammonium was on the list of exceptions. Lead nitrate. All nitrates are soluble, so soluble. Silver iodide. Iodides were generally soluble, but silver was on the list of exceptions, so it's insoluble. This has been a brief tutorial on electrolytes, acids and bases, and water solubility.